comfortable? How can you stand being sideways like that? It's fine? Okay, all right. It's all good. Most of my teaching this semester is sideways, is quirk of the rooms. So this is the big theorem at the end of the section we're currently working on. And so I'm just going to state the end at the start, and then we're going to chip away at proof, basically chip away at the proof and explanation for this theorem. But I wanted the theorem to be at the start because I want to emphasize this is the big picture that I want you to get from this section. All right? And the big picture is this. If you've got a differential form, p dx plus q dy, on a domain D, the following are independent. All right? Number one, path independence. Of omega on D, meaning that the integral over gamma 1 of omega is equal to the integral over gamma 2 of omega for, let's say coterminal gamma 1 and gamma 2. So by coterminal, I mean they both are doing what? They're going, they've got the same starting and ending point. They can cross too. I'm just not crossing them for the sake of the picture being easier to kind of follow. Yeah? All right. Number one, path independence. And number two, the integral around a loop of omega is 0. 3, omega is exact on D, and by that I mean that there exists H, all right, which is a function from D to the complex numbers such that omega is equal to DH, all right, that's exact. And 4, provided D is star-shaped, omega closed on D. And so this right here, what does it mean for omega to be closed? So definition, p dx plus q dy equal to omega, all right, is closed if qx is equal to py. All right, so that makes that differential form a closed differential form. And then finally, furthermore, if omega is closed on region between counterclockwise oriented loops, gamma 1 and gamma 2, then the integral over gamma 1 of omega is equal to the integral over gamma 2 of omega. This is called the deformation theorem. All right. So I want to try to explain to you why these things are true today. We've already started. What have we already explained last class? Do you guys remember? We talked about path independence, and we proved the equivalence of 1 and 2, right? We proved that path independence and integrals around loops vanishing, those are equivalent, right? And so now, what else did we have last time? What was the other big result we had last time? FTC, right? Integral from A to B of, let's say, dH, h of B, h minus h of a, and here this is any path that goes from, from A to B. So we can use this notation, integral from A to B, provided, like the integral from A to B makes sense provided what? Provided that it doesn't matter which path you use, right? So a path independence gives us the ability to express integrals in terms of their endpoints, if you wish. Okay, so let's talk about 3 implies 2 for a second here. So assume omega is exact, right? Omega equals to dh, right? Consider loop in D, right? So we can basically picture it something like this. We start at the point A, we go round, we come back where we started. So B is equal to A, right? A loop. And I usually think of them counterclockwise. So that's a loop. So what's the integral? And we use this symbol here. See this integral with that circle? That just indicates it's a loop integral, right? You don't have to write that. It just helps. And you can also indicate the orientation by putting like a little arrow on that. That's another notation which is used. But anyway, here the point is the integral over omega of the loop is equal to the integral from A to B of dh in this case, right? Which is h of b minus h of a, which, by the way, is equal to 0 because a is equal to b, right? So certainly exact implies that the integral around loops is 0 for the form. Okay. Now, let's see here. Now, and it's also, proof 3 implies 1. Very similar, right? Because if you have 2 paths, right, and the one goes from A to B, and the other goes from A to B, right? So if you have integral over gamma 1 of dh, what do you got? You've got h of b minus h of a, right? But that's also equal to the integral over gamma 2 of dh, if we're assuming. So if we have if we have exact, definitely we can get path independence. Again, it's a simple, really corollary to the FTC for the integral, right? Okay. How about 3 implies 4? By the way, I'm not being logically minimal here by any stretch of the imagination. Of course, the easiest way to prove the equivalence of 4 things is to do what? Prove 1 implies 2, implies 3, implies 4, implies 1 again, right? So I'm not going down that path. Oh. What you need the stickies? Oh. Oh, okay. So you're adding sticky notes to your notes as a way of, hey, that's not a bad approach. I don't know. Yeah, see, I forget about this, Audric, but like when I was in school, that's one of my ongoing like sort of meta narratives was improving my note-taking strategy. You know?
I just feel like if I'm listening more, I'll get it more. Like, if I'm writing, I'm not listening to you. That makes sense?
There is a balance between writing and listening. But okay, 3 implies 4. So in other words, prove exact implies closed. All right? So if omega is exact, right? If omega is equal to dh, remember dh is partial h, partial x dx, plus partial h, partial y dy, by definition of dh. That's the definition of differential. And that's going to be, by our notation, p dx plus q dy. Right? So the only way this can be true, so this gives p is partial h partial x, right? And q is partial h partial y. Thus, what's qx equal to? Well, qx, of course, is then partial x of what? Of partial h partial y. But remember, just like we needed on the test to prove holomorphic implies harmonic, we need to commute the partial derivatives. So this is partial y, partial h partial, is that a what? Oh, I think Clairaut's theorem, yeah. And then what do you have? Well, that's partial, that's exactly partial y of p, right? So that's py. Therefore, you have that the differential form is closed, right? Because that's the closed condition. That's what we mean. That's our definition of closed. Okay? Therefore, omega equal to p dx plus q dy closed. So there you go. 3 implies 2, 3 implies 1, 3 implies 4, right? And if you notice, 3 implies 4, we did not need the criteria star-shaped, right? Didn't come into play here at all, okay? So it's actually the reason this provided star-shaped condition right here, that's actually necessary for the converse direction for 4 implies 3, as it happens, okay? All right, let's talk about, now the one that's a little bit trickier and we should talk about, we should unravel, because this also gives us a calculational procedure, another insight into the nature of the complex integral, is the problem of 1 implies 3. Okay, let's do 1 implies 3 here. Let's work on that. So we assume that omega, which is p dx plus q dy, is path independent. All right? So what does it take to show 3 holds? What do I have to do? I have to prove there exists an h such that dh is equal to omega. Right? I have to prove that there exists what's called a potential function. Right? This h you could call a potential, yeah. A potential for omega. So we need to prove that there exists h from the domain to the complexes such that dh is equal to omega, right? Now that is equivalent to saying that partial h partial x is what? P. And partial h partial y is q. We need those 2 conditions. We need to find a function whose partial derivative with respect to x is the p, partial derivative with respect to y is the q. So here's the construction. Let A be, so also, my bad, I forgot. What do we need for this case? Oh, wait a minute, I don't need that yet. Ooh, oof, 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 oof. Second here, I feel like I've something, I'm forgetting something. Oh, I'm not forgetting something. I'm confusing my. So I'm currently working on what I've called lemma 3.2.6. Yeah, okay. So I was thinking about a future one where I need to assume star-shaped. I don't need to assume star-shaped for this, okay? Fine. So let's go on here. So what we're going to do, let A be a element of the domain D and define h of z equal to the integral from a to z of p dx plus q dy. And why can I make that definition? I've assumed what? Path independence, right? And D is a domain, which means what? D is open and connected. So for any, this works for any z and z, for all z in D. This makes sense because we can draw a picture, right? This could be A, right? This can be Z. And path independence of omega on D allows me, right, to find a path, right? Whatever, you could make it, I think I allowed it to be formed by piecewise, really an arc, if you like, as a union of piecewise smooth curves. I've used line segments to make my picture, but the point is, it doesn't matter which one, if you did that one, or if you did, smooth it out and do the smooth one, that's kind of the same. Either way, we get the same answer, right? Because path independence is assumed. So what do we have to show? So let me make my picture over here a little bit less annoying. Fine, I'll stick with this. It's not big enough. So what we can do, so I'm just going to make it simpler. So here's my A, here's my my point, another point. So let Z be curses. I always forget how to say this here. Yeah, so fix a point B equal to x naught plus I y naught. And so what I want to do is I want to study, my goal is to study partial derivatives of h at z naught, x naught plus I y naught, right? So I got this curve, whatever it is, like that. And then I can look at points close by, right? I can look at a point like here of the form, say, x naught plus iy, or I can look at a point over here, say x plus iy naught, right? And I can look at the line segments which connect horizontal one here, right? Or the vertical one there, right? And if I look at h of x naught, well, let's see here. H of x naught plus iy should be equal to what? The integral from a to b of p dx plus q dy, right? Plus the integral from x naught plus iy naught to x naught plus iy of p dx plus q dy, right? And similarly, we have h of x plus I y naught would be the integral from a to b of p dx plus q dy plus the integral from, x naught plus I y naught to x plus I y naught. So all I'm doing is saying, do integral along the purple curve and then the green curve, or you do the integral, along the purple curve and then the red curve, right? But I could say a little bit more. Let's just call this, first thing Pac-Man, just to be lazy. All right, so what this is equal to is Pac-Man. So we got Pac-Man, and then we need to actually get into the details of the red curve. So like the red curve has equation x equals to t, all right, and y is equal to y naught. That's a parameterization of this for x naught less than or equal to t, less than or equal to x, right? That parameterizes.
How do you have these two, like you called that Pac-Man and you called this you have a lot of Pac-Mans going on.
They're the same Pac-Man. It's the same purple curve to get from a to b.
The integral from a to b of p dx plus q dy is equal to that whole thing up there too.
Yeah, I'm saying that the integral from, I'm not done with these yet.
Oh, okay.
The integral from this to that is this integral plus that integral. Integral from here to here is this integral plus that integral.
Okay.
I'm not done yet. So this is plus the integral from, say, x naught to x of, and by the way, in the red, let me finish the red here. Dx is dt, right? Dy is 0. So for this integral, the dy piece is gone, and we just got p dx. But more specifically, that's p of what? P of t, comma y naught dt. That's what happens there. And the other one gives you plus the integral from y naught to y of q of x naught, comma t dt. See, because the parameterization of the green curve here is x equals to x naught, y equals to t for, 0, excuse me, not 0, but for y naught less than or equal to y less than or equal to, golly, t less than or equal to y. And here, of course, dx is 0 and dy is dt. So the vertical integral just picks up the q dy term in a non-trivial sense, all right? So then you look at this equation, right? And if we have this is equal to that, well then this gives us that partial h, partial x, rather partial h, partial, yes, partial h, partial.
You have partial x h. You're saying it has no dependence.
I'm saying that I made a typo here. This was supposed to be x plus y naught. And I made the same typo here. The point was that was the red curve, so it goes from x naught plus iy naught to x plus iy naught.
Yeah.
I'm sorry, if that's what you were asking me about before, my apologies. I couldn't see it at the time. And here, I want x naught plus iy. My bad. I am so sorry, guys. There, now it should make more sense. See, because the second line, I'm talking about the integral on the purple, then plus the integral of the vertical. The endpoint here is x naught plus iy. So with that, with that adjustment, partial h partial x, right,
Yeah.
should be equal, so partial h partial x should be equal to, partial x of the integral from x naught to x of p of t comma y naught. And what's that? Well, fundamental theorem of calculus says that that's p of x comma y naught. So therefore, partial h partial x at x naught y naught is just p of x naught y naught. And likewise, partial h partial y is equal to q. See, because if I differentiate this with respect to y, then I get the derivative of the green thing by fundamental theorem of calculus. I'm just varying the second component, so that's the partial q partial y, right? That's partial q partial y. Excuse me, that's, I'm an idiot. That is q of x naught y, because when we do the fundamental theorem of calculus, we're integrating a variable bound. We're differentiating with respect to the variable bound. And so we just plug that y into there. That's how it goes. Now, so yeah, partial h partial y. Now, of course, what else am I doing? I'm saying that Pac-Man has no x and y dependence. See, Pac-Man is just depending on x naught y naught, but it doesn't depend on the x and the y. So when I do the partial derivative with respect to x or with respect to y, the Pac-Man drops out. See, that's part of the idea of the proof is like that. X and y are just depending on how far you go over or up from the Pac-Man. I mean, from that point B. All right, so there you go. That's the proof that 1 implies 3. And it does a little bit more. So notice here, as an application, right? We can construct h of z as equal to the integral from 1 to z of r omega, right? So if we want, dh to be p dx plus q dy, we can just set up h as the integral from, I said 1, but I should say a, right? Okay. All right. Let's see here. How about 4 implies something else? Let's see here. Let's try to do closed implies exact, all right? So that was 4 implies 3, which could be restated as closed on star-shaped implies exact. All right, so this one involves a sneaky little picture. All right, so try to set it up for us. So here we have here's our point A, right? And here's our point Z naught. And put another point up here too. I'll put another point over here. So see here. So I make, I'll put the z naught up here. It's a better, easier place for me to label it. So there's two triangles I can form from this, all right? I can form this triangle here. Right? Or I can form this triangle here. All right. So I will call the upper triangle T2. And the lower triangle T1. All right. And we're going to assume that D, so what we're doing is we're assuming D is star-shaped and that we have a closed form on D, right? So D is star-shaped and we have a closed form omega on D. And what are we trying to do here? Well, I get, so I don't have, I was like, why can't I just use it? I did prove, why can't I just prove it like I did last time? Well, what's the problem? Last time we had the assumption of path independence, right?
Yeah.
At the moment, I just have that it's what? That it's closed. Do I know closed implies path independence?
I think you have
See, I have not proved that. I do think it is true, all right?
trying to see. Should 3, 2, 3, 1, 3, 4.
Okay, so I have not proved that.
No, you should 3, 1. Yeah, 3 implies 1. You say that's exact. We don't have that it's exact.
No, I do not. I have not proved 4 implies 1. If I had 4 implies 1, then we could just piggyback on the
Yeah.
previous proof we just did. Okay, so I'm going to focus here on this one, partly because the proof is a little bit interesting. So here we go. So star-shaped domain, we're assuming, PDX plus QDY is closed there, right? And, okay, great. We're going to let h of z is going to be the integral from a to z, all right, of PDX plus QDY. So this a to z, this is the interval, the line segment rather, from a to z in D. How do I know that that's a subset? How do I know that a to z is a subset of D? We're assuming that here A is the star center. We're assuming A is the star center, so with that assumption, we know that this line segment from A to Z is a subset of D. All right. So then we can apply Green's theorem on the triangle T2. Now, what's the boundary of T2? So it is the line segment from A to Z naught, right? Unioned with Z naught to, let's say, the point 2. Let me call this Z2. I guess I should call it Z2 and Z1. My picture in the notes is kind of lazy. I've got a 1 and a 2 there, And so we go this way, right? That way. Wait a minute, am I going, that's counterclockwise, right? Yep, counterclockwise. And then I got to go from Z2 back to A again, right? That's the positively oriented boundary of triangle 2. Green's theorem then says that the integral, the integral over the boundary of T2 of PDX plus QDY, right? Yeah, of what? Of partial q, partial x, minus partial p, partial y, which is what? But remember, closed. Q is closed. What does closed mean? Remember what closed means? Closed means that qx is equal to py, which is to say that the area integral is the integral of 0. Yeah, so this is equal to 0, right? Yeah.
But that's not just say that the area is 0.
No, I suppose not. But now partial t2, this is what? Again, it's this union, right? So we've got the integral from integral over a to z naught of, omega, plus the integral from z naught to z2 of omega, and then what? And then we can do minus the integral from a to z2 of omega. See what I did? I used the fact that the integral is oriented, so if I reverse the curve, then it gives me minus of the integral. So this would be the integral from a to z2. So like the natural orientation goes from z2 to a, which is minus the integral from a to z2. All of this is equal to 0. But this, by definition, what we're looking at here, then,
Why can't we say that because it's a closed loop? Like, why can't we just say like it's going to be 0 if it's a closed loop?
because we're not working on that right now. We're assuming closed, and we're trying to prove it applies exact. I
Yeah,
mean,
but we have that. We said that we used green theorems to show that it was equal to 0, but couldn't we show that it's because it's a closed loop on the star shape that it's also equal to 0?
well, I'm not assuming that the theorem is known already. I'm trying to prove.
Okay.
I'm proving the theorem bit by bit here. So what this gives us then is that the integral, from z naught to z2 of omega, well, that's equal to h of z2 minus h of z naught. But this is z naught to z2, right? It's just like the previous proof. It's a vertical, like z naught to z2. So we can let z2 equal to, x naught plus iy, right? Whereas z naught is x naught plus iy naught, right? And so z naught to z2, this has parameterization, x equals to x naught, y equals to t, for y naught less than equal to t less than equal to y, dx is 0, dy is dt. So this right here, guys, is exactly the integral from y naught to y of, what is it? Well, remember, so just q of x naught comma t dt, and that's equal to what? That's equal to h of, x naught plus iy minus h of x naught plus iy naught. So if you want, you can take this and, one thing you could do would just be to divide by, well, anyway, the point is if we partial differentiate this with respect to y, we get what?
Q x naught comma t.
Partial q, partial y, right? I'm sorry, I may have lost my way here. Give me a second. I'm an idiot. So I'm a dummy, like moron. So this, if I differentiate this with respect to y, right?
It just pops out Q.
Yeah, that pops out q, right? Exactly, that pops out q of y, comma, good grief, x naught, comma y, and that will be equal to partial h, partial y.
Oh, and then you get exact. Yeah.
So that's part of it.
Yeah, that's
And then if you look at the red triangle, you can similarly prove,
Yeah, that P of x, y naught is equal to partial h, partial p, or partial x.
right, partial h,
And then you have the exactness.
which then proves that, yeah, this is exact. So it's the same construction of h as the previous proof. It's just this time we use Green's theorem to get what we want.
Okay, so my question about two, like having two, like I know these are all like the following are equivalent, but like if you didn't know that the following were equivalent, like couldn't you like just skip the middle bit because you have two?
I don't understand your question yet. What are you saying?
So from once we get Green's theorem that equals 0,
Yeah,
you know, that's how we got that the integral p dx plus q dy is equal to 0.
right.
I'm saying that we're doing an integral over a closed loop, and that's equal to 0. We know that's equal to 0 because from A, you're going from A to A on that blue triangle.
So what are you starting with? What are you assuming is known?
2.
Well, if 2 is known, then yes, the integral around a loop is 0. That's, if you're assuming 2, then 2 is true, yeah.
See, but I thought 2 is just true, like, period.
No,
Oh,
it is not.
okay.
No, the integral around every form, around any loop, is not 0 for any form. Let's talk about that.
I'm not just taking physics stuff and saying, solve.
In fact, that's one of our fundamental misunderstandings that we must address. We must, in fact, understanding that is a large part of this course. That's actually like one of the fundamental issues that we need to address. So here's the example. So theta, right? So example. The point of this example is exact does not imply closed. Excuse me, other way around. Closed. The other direction is actually true. Closed does not imply exact. Always, in general. All right, so consider theta. This is the inverse tangent of y over x, basically, right? And, well, it's either this, it's this plus, plus epsilon, where epsilon is either equal to 0 or 180 degrees, or pi, rather, depending on whether you're in quadrants, As long as you're away from where x is equal to 0, this is the formula, right? So, long story short, d theta is what? Partial x of inverse tangent of y over x, dx plus partial y, derivative of inverse tangent of y over x, dy. And so you work it out, what you get is minus y dx plus x dy over x squared plus y squared. All right. So anyway, you could take this as a starting point, okay? You can start with omega equal to, minus y dx plus x dy over x squared plus y squared. I mean, let's suppose we start there. You could definitely do that, right? This is a form. You can start with this, right? I'm telling you where it came from. It came from taking the differential of the angle function, okay? It is therefore totally unsurprising that this is closed. So here you can check. It says this is closed because you can check that partial y of minus x over x squared plus y squared, partial y of I'll get it right eventually here, minus y, so this is the x component, is equal to the x derivative of the y component. In other words, py is equal to qx, okay? So you can check it's closed, all right? So let's let gamma be unit circle, yeah?
Can you just say from here that you can show that partial x, like you can show exactness this isn't exactness from that statement there? Because we have py equal to qx, you take the partial derivatives.
It's closed.
Yeah, that you just showed it's closed, but when you test for exactness with py equal to qx, it doesn't.
No, py equal to qx doesn't test for exactness.
No, what I'm saying, you can test for exactness from there.
You can't, no. That's the closed condition. Exact is something else. Exact is, does there exist an h such that omega is equal to dh? And we're not there yet. But we do know that if it is exact, that implies that the integral around a loop is 0, right?
Yeah.
So if we can show that the integral around a loop is not 0, it's not exact. Well, a nice loop to consider is the unit circle, right? The unit circle has x equals to cosine t, y equals to sine t, right? So dx is minus sine t dt, and dy is cosine t dt, right? And so what's omega when we evaluate it on the unit circle? So the integral of omega over the unit circle is going to be the integral from 0 to 2 pi, right? Let's see here, minus y is minus sine t times minus sine t dt plus cosine t times cosine t dt divided by x squared plus y squared. What's x squared plus y squared?
1.
Yeah, it's 1, right? So explicitly here, it's cosine squared t plus sine squared t. But you see what happens.
But you get a dt. Oh, no, I'm sorry.
So you see what happens. You've got sine squared plus cosine squared upstairs times dt. Yeah, the integral, it's dt.
Yeah.
So we have the integral of dt from 0 to 2 pi, which is what?
Just t.
It's, yeah,
Oh, from 0 to 2 pi?
right.
Oh, yeah, that'd be 2 pi.
2 pi, which of course is not equal to 0, right? Therefore,
Not exact.
omega is not equal to dh on a set which contains gamma. Right? I mean, now here's the tricky thing. You're like, well, but didn't you just say that it's, where is it closed? Where is this form closed? Where is p partial q, where's qx equal to py here? Where is this true?
On omega?
Omega. No. What domain is this true?
Oh, is that true on? From pi to minus pi to pi?
Nope.
Tangent?
Nope. What complex numbers is this true for?
Oh, okay, so you have the modulus, or the modulus squared,
I mean, it's true on the domain of omega, right? What's the domain of omega? It's the complex numbers without 0. Right? It's the
oh, yeah.
it's the punctured plane. And is that star shaped?
No.
It's not.
Can't
Right.
go from quadrant 1 to quadrant 4.
So this is an example. So, that's not star shaped because if you're missing this, if you're missing 0, wherever you make your star center, right?
Yeah.
You can't get this over here. It's, you can't get if A is the star center. But We could also look at it this way. Omega, omega is closed on star-shaped slit complex plane, right? And so if you want, you could use 1 as a star center, right? Yeah. And you'd have, the integral of omega from 1 to z is equal to, what is it? Well, that's actually the integral from 1 to z of d theta. That's what that is. It's the differential of theta, right? So what that is actually is the argument of z minus the argument of 1. What's the argument of 1? What's the standard angle of the positive real axis? It's 0, right? So straight up, guys, this is a formula for the argument. We can do the integral. We can define the argument. We could actually define arg z to be the integral from 1 to whatever z you're interested in of, this thing, minus y dx plus x dy over x squared plus y squared. And if we had more time today, I'd love to work out an example where we actually calculate the angle using this. I think that could be really cool, right? Like, here was what I was going to do if we had slightly more time. If you wanted to, like, what's the angle of, like minus 1 plus I, right? So if I'm starting at 1 and I want to get to here, maybe I could try. This might be truly horrible. Like, the integrals involved could be truly horrible. I could break it up into 2 paths, right? I could, like, do this line integral, then that line integral for that form, and see what happened. But I think those integrals could be kind of hairy. So I'm gonna try it when I get a couple minutes, but I haven't tried it yet. So anyway, the thing I haven't talked about yet today, of course, that was on the theorem that I stated at the start of class, is this deformation theorem, right? So I think I'll talk about that next time. But we should finish up this chapter, I think, and so like next week we'll start the complex integral.